All right, let's talk about batteries. We all use them, but what's really going on inside? Today, we're going to get into the chemistry that actually controls how much power a battery has, not in a perfect lab, but out here, in the real world.
You know the feeling, right? You pop a fresh set of batteries in and everything's zippy and responsive, but then day by day it gets a little weaker, a little slower, until it's dead. So what does dead actually mean, chemically speaking? Well, believe it or not, there's an equation for that, and it's the key to understanding this whole process.
So, at its heart, a battery is basically a tiny, self-contained power plant. It's what we call an electrochemical cell. It's this clever little package that takes the energy locked away inside chemicals and turns it straight into electricity. It's all about harnessing chemical reactions that are just itching to happen anyway.
Now, there are basically two main types of these cells. You've got electrolytic cells, which use electricity to force a reaction to happen. But we're interested in the other kind, galvanic cells. These are the ones where a natural, spontaneous reaction creates electricity. For our purposes today, just think galvanic cell, battery. That's our focus.
Okay, so if you're a scientist and you want to compare different batteries, you need a fair race, right? You can't have one testing in the cold and another in the heat. So they came up with a set of perfect, ideal laboratory conditions. Think of it as creating a perfectly level playing field to measure every reaction's true potential.
And the number they measure on that level playing field is called the standard electrode potential, or E0. This is the absolute best-case scenario voltage a reaction can produce. It's kind of like the sticker price MPG on a new car. It's a super useful baseline, but you know it's not what you're going to get in your day-to-day driving. This is our ideal starting point.
But how do you even measure the potential of just half a battery? You can't. It needs something to be measured against. So scientists brilliantly chose one specific reaction, the standard hydrogen electrode, and just defined its potential as zero, exactly 0.00 volts. It's the sea level of electrochemistry. Everything else is measured as being higher or lower than that.
Okay, so we've got our perfect lab conditions. But as soon as we step out into the real world, things get messy. Your phone gets hot, your car battery gets cold, and most importantly, the chemicals inside the battery are constantly being used up. This is where the ideal model starts to break down.
And this brings us right to the heart of the matter. What actually happens to that voltage as the chemical fuel, the reactants, get used up, and the chemical exhaust, the products, starts to build up? There has to be a way to calculate the battery's power in the middle of its life, not just at the perfect start.
And there is. The tool we need is the Nernst equation. It's named after Walter Nernst, a German physicist, and it is the absolute key. It's the mathematical bridge that lets us walk from that perfect, standard potential in the lab to the actual, real-world voltage of a battery at any given moment.
And here it is. Now I know, it looks a little intimidating with all the letters, but don't worry, the concept is really simple. All it's saying is, to find the real voltage, you start with the ideal voltage, that's E0, and then you subtract a small correction factor that accounts for the messy real-world conditions. Let's break down what those letters mean.
So R and F, those are just universal constants. Think of them as nature's conversion factors that make the math work out. T is just the temperature, simple enough. N tells us how many electrons are doing the work in our specific reaction. But Q is the star of the show. The reaction quotient, Q, is just a snapshot of the chemical balance inside the battery right now. It's a simple ratio of how much product you have versus how much reactant you have.
Now, to make our lives a whole lot easier, since a ton of chemistry happens at standard room temperature, we can just pre-calculate all those constants. And when you do that, the big equation slims down to this much friendlier version. This is the one we'll be using. You can see it's just our ideal voltage minus a little correction.
All right, enough with the theory. The only way to really appreciate how powerful this thing is to see it work. So let's take a couple of classic battery examples and use the Nernst equation to figure out their real-world voltage.
First up, the classic of all classics, the Daniell cell. You've got solid zinc reacting with copper ions. Under those perfect standard conditions, this little guy reliably produces 1.10 volts. But what happens when the amounts of copper and zinc ions are no longer perfect?
Well, the Nernst equation gives us a super intuitive answer. The copper ions are the fuel for this reaction. So if you increase the amount of fuel, you get a bigger push, and the voltage goes up. On the flip side, the zinc ions are the exhaust. So if you increase the amount of exhaust, it creates a kind of chemical back pressure, and the voltage actually goes down. It's a direct link between what's in the solution and how much power you get out.
Okay, now for a more realistic example. Here we have a cell made of magnesium and silver. But just look at those concentrations. They are way, way off from the standard 1 molar solution. We have a ton of the product, the magnesium ions, already built up, and we have very little of the reactant, the silver ions, left to work with. What do you think is going to happen to the voltage?
Let's walk through it. First, we look up the standard potential, our starting line, and it's a huge 3.17 volts. Second, we look at the balanced reaction and see that 2 electrons get transferred, so N equals 2. Then, for step 3, we just plug all our numbers, the concentrations, the N value, into that simplified Nernst equation. And finally, we just solve for E cell, the real-world voltage.
And look at that, 2.96 volts. That's a pretty big drop from the ideal 3.17, isn't it? This isn't just a random number. This is the Nernst equation, precisely calculating how much power the battery has lost because the chemical fuel is low and the exhaust is high. It's the math of a dying battery.
And this all leads to a really deep and beautiful idea. The voltage you read on a battery, it's not just a measure of power. It's a measure of how far away from chemical balance, from equilibrium, the system is. The higher the voltage, the more the reaction wants to happen.
So every time you use a battery, the reaction moves a little bit forward, the reactants get consumed, the products build up, and, just as the Nernst equation predicts, the voltage slowly drops. The whole system is just gradually sliding down a hill towards its final resting point, equilibrium.
And what happens when it finally gets there? When it reaches perfect chemical equilibrium? Well, the push is gone. The desire for the reaction to happen disappears. And the cell's potential becomes exactly zero. That's a dead battery. It's not empty of chemicals, it's just perfectly balanced.
Now, here's the really mind-blowing part. The Nernst equation also lets us connect a battery's ideal standard potential directly to its equilibrium constant, Kc.